Now let's talk about inverses and how we use matrix inverses to solve systems of linear equations. To start off with, the inverse of a square matrix A, which is an n by n matrix, is denoted A to the negative 1. It's important that we're only going to talk here about inverses of square matrices. So A has to be n by n, a square matrix, to have an inverse. There exist other types of inverses or similar generalizations for non-square matrices, but we're only going to talk about square matrices here. The inverse, A inverse, is a matrix such that when we multiply it by A times A inverse, that equals the identity. And we can actually do this multiplication on both sides. So A inverse times A also equals the identity. And one of the most important elements of matrix inverses is that these don't necessarily have to exist. We say that a matrix is non-singular if the matrix has an inverse, and it's singular if it does not. So it's important terminology there. It is non-singular when it does have an inverse, and it is singular when it does not have an inverse. And there are a lot of equivalent conditions to describe when A has an inverse or doesn't. The one we'll list here, and there are some more that will come up in later videos, is that the inverse of A exists if and only if we cannot find a non-zero vector x such that A times x equals all zeros. So remember, A is a matrix here. It's a square matrix, n by n. We multiply by some vector x. That gives us another vector. And if we can't find any vector x such that this product here equals all zeros, that is except for the trivial solution, which would be setting x equal to 0. If this is not true for any other x, then the inverse of A will actually exist. And there are some important properties about the inverse. And here we're going to let A and B both be square matrices and both be non-singular so that their inverse in both cases exists. First of all, the inverse of the inverse is just A. Right? And this should be pretty easy to see because if we multiply A inverse by something and this equals the identity, this something here will be the inverse of A, but of course by the definition of the inverse, this is just A. So this thing here is the inverse of A inverse. Similarly, if we invert a product of two matrices where both these matrices are themselves non-singular and square, this equals the same product just in the reverse order. This again is pretty easy to show because if we have A times B and we multiply it by B inverse A inverse, well, first these two terms cancel, right? This just becomes the identity. So this equals A times A inverse, which equals the identity. So this proves that the inverse of A times B is just B inverse times A inverse. And finally, the inverse of A transpose is actually just equal to A inverse transpose. It doesn't matter which order you do the inverse or transpose in, this is the same matrix. And for that reason, we frequently, or sometimes at least, will denote it as A inverse transpose because it doesn't matter which one of these two we mean, they are in fact equivalent. Now, one of the most common ways to use the inverse is in solving sets of linear equations. So the set of linear equations we had in the very first video introducing linear algebra. And remember, we could write these linear equations as ax equals b, where a is defined like this, x is the vector of these two unknowns, and b is the right-hand side. And now, going back to the definitions of matrix multiplication, it should be apparent that this product does in fact give you a compact way of representing this set of linear equations. Now, one of the questions we might want to ask, remember, is what are values of x that actually satisfy this equation? And we did it before by actually adding and multiplying these equations together, but in matrix form, we can just use the matrix inverse to solve an equation like this. Now this is giving a solution kind of at a high level because we're not actually talking about computing this, but computer software is very good at computing inverses, so we'll just leave things as inverses. So how does this work? Well, first of all, we have our equation ax equals b, and what we really do then is we multiply both sides of this equation by A inverse. But of course, this term here just becomes the identity. The identity times any matrix, and x is a vector here, which is also a matrix. The identity times x just equals x, so the solution we have is just going to be x equals A inverse times b. Now again, what we described here is not an actual way to solve this problem, right? We just described a way of writing the solution as x equals A inverse b. If you actually want to compute what the solution is, you need to either invert that matrix or somehow solve those equations. And that's a little bit more complex, but it turns out the way a computer actually does this is very similar to that first process we described of multiplying certain elements of the matrix or certain rows, certain sets of equations by other constants, adding them together or subtracting them, and canceling terms out. That's actually exactly how computers solve these equations. So for our purposes, we're not going to worry about how we actually compute the solution, because this solution we can type into a computer program and it will tell us what x actually is as long as we have values for A and for B.